Hi, in this video we'll be learning about pitch. So, what is pitch? And why does this sound higher than this sound? Pitch is how we perceive the frequency of sound waves. A sound is caused by the vibration of air molecules, and it travels in a wave-like manner. The length of one cycle of a sound wave is known as its wavelength, and it's represented with the lambda symbol. Frequency is the number of cycles that occur per second in a sound wave, and frequency is measured in units called hertz. Higher pitched sounds have a higher frequency, which means a shorter wavelength and more cycles per second. Lower pitched sounds have a lower frequency, which means a longer wavelength and less cycles per second. The average person with normal hearing can associate pitch with sounds from approximately 20 Hz to 20,000 Hz. So now that we know what frequency is, how exactly is frequency related to pitch? The unit of pitch is called a mel, and we can examine the relationship between pitch and frequency on a mel scale. The mel scale uses a reference point of 1000 Hz at a particular volume, and this reference point is equal to 1000 mels. Here's a graph of one formula for a mel scale. As you can see, the relationship between frequency and pitch is curved, somewhat like an S, rather than a linear relationship. The blue point represents the reference point at 1000 Hz, which is equal to 1000 mels. The pink point is at 2000 mels, and its frequency is slightly larger than 3000 Hz. The tone at 2000 mels is perceived as twice as high in pitch as the 1000 mel tone. So far, we've learned what frequency is, and that pitch is how we perceive the frequency of sound waves. We've also looked at a mel scale to see the nonlinear relationship between frequency and pitch. The last concept we'll learn about is audible distortions. Audible distortions occur when you hear frequencies that were not present in the stimulus that entered your ear. This graph represents an example of distortion products. There are two pure tones being played outside a person's ear at the same time. The first one is F1 at a frequency of 800 Hz, and the second is F2 at 1000 Hz. The first distortions we'll look at, labeled in purple, are oral harmonics. The 800 Hz tone produced a distortion with a frequency of 2 times 800, or 1600 Hz. The 1000 Hz tone produced a distortion with a frequency of 2 times 1000, or 2000 Hz. The second type of distortion we'll look at, labeled in green, is a difference tone at 200 Hz, which is the difference between the frequencies of the two tones being played. Labeled in orange, we can see a summation tone at 1800 Hz, which is equal to the frequencies of the two tones being played added together. The last type of distortion illustrated here is the cubic difference tone at 600 Hz, labeled in red. This is equal to 2 times F1 minus F2. This distortion product is particularly important to audiologists because it is used to assess inner ear function in newborns by testing otoacoustic emissions. Otoacoustic emissions are sounds produced in the inner ear, which can occur spontaneously or be evoked by certain tones. The types of distortions that one hears can depend on multiple factors, including the volume of the tones played and how close in frequency the two tones are. These distortions can be explained by the way in which a sound wave with more than one tone travels down the basilar membrane of the cochlea, which is the part of the inner ear where we convert sound waves into neural code that can be passed on and interpreted by the brain.